Hi, everybody. In this lecture, we are going to study the class NP. So remember that we saw regular languages, we saw context-free, then we went to study desirability, then we saw P, and now we're going to see NP. Let us begin with a definition, then we're going to see several examples. We're going to define NP in the following way. A language is in NP if you can find an integer c and a Turing machine m which runs in time n to the c, so it's polynomial in the input length, such that a string is in L if and only if there exists a y called a witness whose length is polynomial in the input length. So the length of y is at most length of w to the c, and m accepts w y. Okay, we're going to see several examples of this, but for now, let us remark that NP means non-deterministic polynomial or power time, and the non-deterministic part refers to the exist y. Please do not confuse NP with not P, okay? The N does not stand for not. Some authors think it does, but it does not. It means non-deterministic. It's similar to the N in the NFA, which are the non-deterministic finite automata. So the first claim is that P is a subset of NP. Okay, and now, what's the proof for this? It's a one-line proof. We can just ignore y. Okay, if I remove y here, m is not even looking at y, then L is in NP if there exists an integer c and the Turing machine runs in time n to the c and decides L. Okay, so let us see the proof with a slightly different notation to tie back to our notation for P. Let us see again why P is a subset of NP. Here is the definition for NP that we saw earlier. What was our definition for P? Well, our definition for P was the union over C of time n to the C, okay, which is the same thing as saying that there exists an integer C such that L is in time n to the C, which is the same thing as saying that there exists an integer C such that there exists a machine M that runs in time n to the C and M decides L, which is the same definition that we gave for NP, except for the exist y part. Okay. One could also define NP in a similar fashion as this if you define n time n to the c, but we have not done that. So here is our definition of NP, and then we're going to see that many problems that we saw earlier are in NP. For example, I claim that 3SAT is in NP. So the input here is a formula, phi. What is y? Y is a truth assignment. Truth assignment for the variables. What's the length of y? What do you think? Remember, you can pause it. You should pause here if you see a question mark and think about it. The length of y is at most the number of variables, which is at most the length of the input. What does m need to check? If every clause is satisfied by y, this only requires you to go through length of phi clauses, and so the computation runs in polynomial time. You're done. This shows that 3SAT is in NP. Similarly, click is in NP. What is y in this case? Is a set of nodes. The length of y is at most the input length, and m needs to check if every pair of nodes in Y is connected. How many pairs do you need to check? Well, quadratic at most in the input length. This is at most t square pairs for this t here, and this is a polynomial time computation. Subset sum, same story. What is Y here? Is a subset of the AIs. The length of Y is at most n, which is at most the input length, and M just needs to check if the sum is equal to t. So how many numbers do you need to sum? At most length of input numbers. So this is a polynomial time computation. Tricolor, same story. Y can be a coloring. Coloring is short, and checking if the coloring is correct is a polynomial time computation. Okay, and now the big result in this area is this completeness result. It's called the Cook-Levin theorem that shows that 3-sat is in P implies that P is equal to MP. Okay, the meaning of this is that if 3-sat is in P, then arbitrary MP computation can be done efficiently. And this is somewhat surprising because you go from one problem, namely 3-sat, to arbitrary computation. However, maybe it's not so surprising, right? Because, well, computers are made of OR and NOT gates, right? That's what 3-sat is. So, you know, you can code up pretty much arbitrary computation with 3-sat, and that's what the proof does. Okay, still, it's pretty cool, and it's a cornerstone of complexity theory. The really important thing of this theorem is that you obtain a problem like 3-sat, which is a very, very simple. Okay, and it's very convenient for reductions, as we just saw. In the previous lectures, we saw that it is convenient to reduce 3-sat to other problems. So we're going to define a language to be NP complete if it is in NP, and if it has the property that if L is in P, if L was easy, then also P is equal to NP. And the claim is that 3-sat is NP complete. Why? Well, we saw earlier that 3-sat is in NP, and 2 is the Cook-Levin theorem, which we're going to prove later. Okay, so 3-sat is NP complete. 3-sat is our first example of an NP complete problem. But there's more. Remember the definition of NP complete. It has to be in NP, and if it's easy, then all of NP is easy. This fact allows us to obtain other NP complete problems. If you have a language L, which is in NP, okay, but 3-sat is polynomial time reducible to it, then L is also NP complete. Okay, to show that something is NP complete, it's possible to show that it's in NP and to reduce 3-sat to it. Why is that? So we have to prove 1, which we already have. We have to prove 2. We only have 2 prime. So how do we prove 2 from 2 prime? Well, assume that L is in P. Then what happens? By 2 prime, we have the 3-sat is in P, right? And now what? P is equal to NP, by the Cook-Levin theorem. Okay, this is the fact that we just showed. If a language is in NP and you can reduce 3-sat to it, then it is NP complete. Okay? Nice corollary of this is this claim that all that we saw, like click, subset sum, and tricolor, they are all NP complete. What's the proof of this claim? Well, we showed 1, that they are in NP, and we show 2 prime. We show reductions of 3 SAT to each of these problems. So each of these problems is NP complete. There's nothing special about 3 SATs. Any of them can be used for the theory of NP completeness. Okay, let's recap. L is NP complete, then it has the property that if L is in P, then P is equal to NP. Equivalently, if you believe that P is different from NP, then also L is not in P. So 3 SAT, click, subset sum, tricolor, they're all NP complete. And in the sense above, they are the hardest problems in NP. If there is anything in NP which is not in P, then in particular 3 SAT, click, subset sum, tricolor, they're not in P. What else is NP complete? Well, there's many other problems that people care about. Okay, in fact, entire books have been devoted to listing NP complete problems. Some problems can be found among puzzles and game. We are not going to list a few, just to see the spread of NP completeness. And there's a technical remark that all these puzzles and games have to be generalized to boards and levels of arbitrary size, okay? So when you play a game like chess, you have a board like 8 by 8. Complexity, has to work with arbitrary input trends. So you have to think of generalized chess in which you play larger and larger boards. And this is generally not a problem. Most or all of these games and puzzles very naturally lend themselves to generalization to larger and larger levels and puzzles. Let's first see a few puzzles. So one is Sudoku, right? This is a very popular puzzle in which you have this 9x9 board, which you have to fill the numbers so that every row has all the numbers from 1 to 9, every little square same, and so on for the columns. You can generalize this to larger and larger boards, okay, with numbers from 1 to n. And then given a partial board, the question is, can you complete that board? Okay, so this question is NP complete. So when you see someone who's on a bus doing a Sudoku puzzle, is actually trying to solve 3 SAT, okay? Trying to solve tricolor, okay? All these things are equivalent. Peg solitaire, in which you make pegs jump. Mastermind, another puzzle game. They're also NP complete. And there's even video games, okay? Tetris, the famous puzzle game in which you have to stack blocks that come from the top, and you clear lines. If you fill here, you clear the lines. If I give you a sequence of blocks, okay, of different shapes, and you want to know if there's a way to clear the level, the question is NP complete. Another cute one is Lemmings, a fantastic Amiga game in which you control these things. You can order them through various things like digging, blocking, building staircase, and you have to save them. So if I give you a level with some constraints, as in the game, on how many they can dig and do other things, knowing if the level can be completed is an NP complete question. Another one that was done more recently is the Super Mario. This is just a popular Nintendo character, so you can build a level. So knowing if a level can be beat is NP complete. So just to clarify what this thing is saying, that if I give you a 3 SAT formula, you can build a level of Super Mario or of Lemmings or a sequence of blocks for Tetris, such that you can clear the level, you can beat the level if and only if the formula is satisfiable. And many others have been done even recently. There is like an whole industry of doing these things, covering like real first-person games, real-time strategy games, all games like Pac-Man, and so on. So Most people seem to think that our world has P different from MP. In this case, P and MP would be different sets. So you have P here. Then you have a subset of MP, which is MP complete. These two things are disjoint because MP complete problems will not be in P. And MP complete will contain something like 3 sat, click, and so on. However, we don't know if this is true. It's quite possible that our world is like this, that everything is equal to P is equal to MP is equal to MP complete. And it would be, a strange and fantastic world. But we don't know how to rule it out. That's where you come into the play. I hope you will be inspired by complexity theory and tackle some of these fascinating questions. Bye now.